Chapter 18 in the Abstract Algebra series is on quotient groups. Problem number 1, construct the Cayley table for D4/n, where n is the set containing the elements e, r, r squared, and r cubed. If we look at D4 is the dihedral symmetries on a square. And those are E, R, R squared, R cubed, which takes care of the top of the square as you rotate it. And then you'll flip it. And once you flip a square, then you could rotate it once, twice, or 3 times, and that would give you 8 different symmetries. So let's examine all of the left cosets of n in D4. In order to examine all of the left cosets of n in D4, I have to let each element in D4 operate from the left side. E times n gives me E, R, R squared, R cubed. Notice that I get the exact same set when the elements R, R squared, and R cubed operate on n from the left. So this is one set. En, since any element in the set can represent the coset, for simplicity, I'm going to let this top row here simply be n. If you look at the second row, these are the symmetries that occur once you flip the square. And notice that Fn operates in the same manner as Frn, Fr squared n, and Fr cubed n. In other words, all of these are the same set. And since any element in the set can represent the coset, I'm going to choose F and let this entire second row be denoted simply by Fn. Again, notice that the left cosets in each row are identical. So really, we only have 2 unique cosets. And as I said before, we will just denote those with n and Fn. So this would be the Cayley table. Notice that we have our 2 elements, n and Fn, represented in the column descriptors here. And then we have n and Fn representing the row descriptors. And n operating on n, I'll just say times. N times n would give you n. N times Fn is going to give you Fn, because remember, n is really En. And if you multiply En times Fn, then according to coset multiplication, I can simply multiply the identity times F, which is F. And this just gives me Fn. Likewise, Fn times n gives me this Fn. And Fn, what would that look like? Well, we have Fn times Fn. And again, using the coset multiplication, I can multiply F on F, or F times F. That gives me F squared. But F squared is simply 2 flips. And 2 flips takes you back to the identity, which is just En or n. Problem number 2. Construct the Cayley table for the group Z as it is, let's say, partitioned by the subgroup 2Z. And of course, we're going to be under addition. Notice that if you take any even integer in Z, and if you add that to 2Z, which is the set of all even integers, the result is going to be another integer, which means that result would also be in 2Z. If you have an odd integer in Z, if you add the odd integer to 2Z, then you are going to get 1 plus 2z. And we're using 1 because 1 would be the remainder. So think about mod 2 arithmetic if you're sort of struggling with that concept. Since every n 2z or n plus 2z is going to be either odd or even, then that means if you add n plus 2z, you're going to force the result to fall into one of two groups. And those two groups would be 2z, which would comprise all of the even integers, and the other group is going to be 2z plus 1. And if we complete the Cayley table, of course, if you add an even and an even, two even integers will give you an even integer, which will place you in 2z. If you add an even and an odd, the result is an odd integer, and so on. For example, 3 and 5 are both elements of 2z plus 1. Because if you divide 2 into 3, the remainder is 1. If you divide 2 into 5, the remainder is 1. So we would place 3 and 5 in 2z plus 1. But notice their sum is 8, which is in 2z. So recall that the sum of two even integers is an even integer, and the sum of two odd integers is an even integer. And of course, if you add one odd and one even, you're going to get an odd result. Problem number 3 asks us to find the order of G slash H, where G is equal to Z36 under addition, and H is the subgroup generated by 15. Well, first, let's identify the subgroup generated by 15 in Z36. If we start with 15, and we add 15. Let me get my pen here. If we start with 15 and add 15, that gives us 30. If we add 15 to 30, that gives us 45, which is 9 in Z36. And we'll just keep adding 15. Of course, we go to 3, 18, 33, and so on. And if I write H if I write the elements of H in ascending order, then this is what we have to work with, and we can see that the subgroup generated by 15 in Z36 has 12 elements, so the order of H is 12. Notice that H consists of all of the multiples of 3, which means I can separate Z36 into 3 groups. Those that result from 0 plus H, which is the multiples of 3. And then, of course, we can add 1 to any multiple of 3, and that would give us this set. For example, if you add 1 to 0, you get 1. If you add 1 to 3, you get 4, and so on. And then if you add 2 to any multiple of 3, we generate this set. Notice that these 3 partitions actually comprise the totality of Z36. Of course, 3 plus H would simply add 3 to any multiple of 3, which puts us right back in the same orbit, 0 plus H. So the order of G slash H is going to be 3. And of course, these are all of the normal subgroups in Z36. Okay. We could have also used the formula from chapter 15. We could have figured out the 12 this way. We could have taken the order of the subgroup generated by 15. We could have used the N divided by the GCD of N and K. That would also give us the 12. But of course, we are partitioning a set that has 36 elements. And if each subgroup contains 12 elements, then that would give us 3 cosets. On problem number 4, we're just simply drawing the partition of Z36 by H, where H is the subgroup generated by 15, and we had 3 cosets. We had 0 plus H, we had 1 plus H, and 2 plus H. Notice that these 3 cosets do comprise the totality of Z36, and notice that they are also disjoint sets, which creates a partition. On number 5, we construct the Cayley table for the subgroups for the cosets, and notice that that H times H is H, H times 1 plus H is 1 plus H, and H times 2 plus H is 0 plus H. I use the word times rather loosely, usually in abstract algebra for simplicity. We simply refer to all of the operations as multiplication. Of course, this is addition. So if you're confused, since we're working with Z, you could think of it as adding H and H, or adding H to 1 plus H. But either way, this is the Cayley table for problem number 3. Problem number 6, determine a subgroup of S3 that is not normal. S3 has 6 elements, and each of those elements represents a permutation on the set containing 1, 2, and 3. And if you draw this out, you would see that these elements also comprise D3, which is the dihedral symmetries on an equilateral triangle. So you have the identity, you have 1 rotation, then you can rotate again. That would take care of all of the symmetries from the top of the triangle. And then, of course, you could flip the triangle and continue the rotations from the other side. Let's consider the subgroup H, which consists of the elements E and F. And we will let D sub 3 represent our group. We'll use G for that. For H to be normal, then GH would have to equal HG for any G in G. So let's choose R. Let's let R be an arbitrary element and see what happens with the left and right cosets. Well, RH ends up generating, let me get my pen here. RH ends up generating RFR squared. But HR generates RFR. Notice that these are not equal sets. And since RH is not equal to HR, then that means that H is not a normal subgroup of S3.